this new normal, new operating conditions phase that we are in right now, where there's a lot of change, there's a lot of what we call extreme VUCA, so this volatility, this uncertainty, this constant change that is affecting us, and there's a lot of requirements for more remote access, secure access to the sites, also less eyes and ears on site, that we can basically see what's happening on the sites. Agility, some of our clients are pushing, through the COVID phase, had to drop their production quite substantially and then have to ramp up, like the mines are now ramping up quite fast again, and they're basically pushing for very high OEE, so they're trying to get the OEE figures up quite substantially. The constant focus on energy optimization and sustainability and carbon footprinting. If we don't look after the carbon footprint, we'll probably have a bigger crisis than COVID, in a few years. So that is always with us every day. Getting the value from data. The session, what we're doing today is all about, we're generating huge amount of data, but how do I use data analysis, to bring more value from it? How do I do it in the cloud where there's lots of processing power? How do I use embedded AI and machine learning to bring some of that value to it? There's a lot of focus on collaboration between various entities as well. So really, how do we work better together with vendors, with OEMs, with system integrators, with solution providers, with end users to bring these solutions to the clients? And then this big focus on more virtual remote operating centers. So you're virtually linking to assets, to the operational assets like mills and crushers and pumps and trucks, but not only assets, like dozers or these continuous miners, but also looking at processes remotely and say, listen, is my process running optimally? Is my advanced process control, my control loops effective? Is my quality where it should be? So in line with this, we put together this whole training session, a webinar series, where we're really trying to stack up, new skills, and cross-skill our clients and ourselves on some of these things, so that we're equipped to understand what value can advanced process control or MES or the various topics bring, and really learning about, how do we use these agile, intelligent technologies that's coming from our vendors, and specifically from AspenTech in modern day industry, and all focused on how do we run our operations faster, greener, longer, and safer. Obviously safety is extremely important. So we run certain key themes, as you can see here, really, starting with basically advanced process control initially. How do I reduce energy efficiency by 10%, or a chemical dosing on a plant by 20%, or how do I push the yield 3 to 4 to 5% in a modern day plant? And there was like 2 sessions on that. You can go and visit them or revisit them. Then focused on asset performance management today, again on that. How do we basically predict an asset failure, and 6 weeks or 9 weeks in advance? And what do we do with that if we have that? How do we optimize the availability of the assets on the plant if we have that type of information available to the clients? Then also we're doing various sessions on MES. So basically, how do we grab lots of data, 500,000 tags from operations and aggregate that and bring metal accounting and operational reporting to the clients, and bring value to the clients that way. So quite a lot of various things that we're covering in this whole series. If I basically just give us a little bit more information about, the 4Sight group. So 4Sight is a group of IT professionals and also OT professionals and business professionals. We're a group of about 400 people, but today we're focusing mainly on the operational technologies group inside 4Sight. And really what we focus on as a team in the 3 businesses is taking the data that we're generating at all our industrial sites right now. The big data is increasing by 5 times currently between now and 2025, and adding technology or intelligent technologies to it, and then looking at the needs of our clients, the people, to define solutions for them, or what we call new business models, to bring value to them, and trying to also leverage the power of the cloud, to do that. So really, that is what this 3 companies in the OT space is really focused on quite a lot. So the type of technologies that we are utilizing here in the center, is technologies like IoT, so Industrial Internet of Things, which is booming at the moment. So again, 35 to about 40% of all IoT devices at the moment is being deployed in industry where we work. And also, using AI, machine learning, deep learning, improvement technologies that's been around for many years, so that we can have structured and not sort of candy store type machine learning being applied. Using new technologies like advanced analytics, multivariate analysis, the theme of today, simulation, virtual reality, augmented reality, all these intelligent type technologies to bring value to the data, to transform the data, into up the stack, like I show here, and also making it available in the ERP system, so that your ERP systems or your industrial facilities are always well aligned with each other. So the first company or the subsidiary in the 4Sight group, in the OT group, is a company by the name Age Technology. So they focused on asset automation and really, they install instrumentation, they connect that to PLC and control systems, PLCs, DCSs, write the code for that to run the controls, to make the plant safer, and then also do the visualization system. So this is really the area where they work in. They are a multi-vendor solution provider, and they bring the best of the Schneider Electric or the Siemens or the Rockwell technology, and they're really doing that integration between automation and between energy or electricity today. So that's what they focus on. The next group is the group that I lead, BluESP. So we focus on asset optimization. We're a reseller and ISP for AspenTech. And really our key focus is taking the big data that's generated from the bottom and transforming that into better information, adding knowledge to it, transforming wisdom, and doing some learning on the data, as we go up the data stack. More about us a little bit later. And then there's a third group, a group by the name of Simulation Engineering Technology, focused very much on asset simulation. So a bunch of 25 simulation industrial engineers also here in the Gauteng region, and the key focus is basically constraint simulation of mining and industrial processes. But also they do optimization of planning and scheduling and the simulation and the control of that. So work a lot in mining, but also focusing on warehousing. They've done work in rail, they've done in financial services as well. So yeah, the digital twin concept is becoming quite a key theme today in what we have to do for our industrial clients. Maybe just a last word on BluESP before we start. So as I said, BluESP, we see ourselves as a very dynamic and agile company of multidisciplinary engineers. So we've got a bunch of chemical engineers, mechanical engineers, electronic engineers, and also data scientists that brings value to the client. We really use technologies, we use AspenTech as a road model to basically, understand what is this new intelligent technologies they bring to market, and how do they bring, for example, AI, machine learning, deep learning into these disciplines of MES systems or advanced process control systems or multivariate analysis, and some of the things that we'll talk about, and you'll see a bit of that today. So working very, very closely with AspenTech on a lot of these things. If you look at the offer set, so we have tools in the design set here. So here at the bottom, and really key focus there is simulation, design, cost, and build associated with a new plant section. If I was going to build a new process of a plant right now, I want to do it the greenest, the most cost effective, and the most sustainable. And there's a whole set of tools that's basically focused on that. And then the next thing is, once I build the plant, I want to operate that plant to its optimum point. So, I want to basically transform that data, aggregate that data into an historian system, make the data available in EROs, so enterprise reporting, operational reporting, do mass balancing or metal accounting associated with that. Also, use, for example, advanced process control in areas where there's very, very complex controls in plants. So that's, some of the things that forms part of basically the operate. And then the last piece is, once I've designed the plant and I'm operating the plant, how do I maintain the plant, its quality and its uptime to the optimum? So yeah, we have tech there, which is like the Intel technology that we talked about last week that predicts a failure well in advance. Or, the key theme of today, how do I find that needle in the haystack? Why is my quality not where it should be, and that's what we're focusing on. And then there's also simulation software associated with that. But I think with no further ado, I'm going to hand over to Raisa to tell us a little bit about herself and also tell us about, introduce the presenters for today. Raisa, over to you.
Thank you very much, Wilhelm, and welcome to you all to our second APM webinar. We will be touching here on multivariate analysis, unlocking the potential in your plant. To introduce us, I am Raisa Khan. I am an APM engineer at BluESP. I have joined early this year and hit the ground running with predictive maintenance for a mining giant. I have previous experience in the steel industry and hold a chemical engineering degree from Stellenbosch University. Next up, we have Laura. Laura has 20 plus years of experience in industrial maintenance and global field service across multiple industries. As a member of the AspenTech Asset Performance Management marketing team, she looks to use this background to communicate how the powerful solutions address the recurring frustrations of customers in the most value-added way. She holds a bachelor's in mechanical engineering from Virginia Tech and an MBA from Indiana University. Next up, we have Kinesh. Kinesh holds a master's degree in mechanical engineering from the University of Pretoria, specializing in gas turbine aerodynamics. Kinesh joined the BluESP APM team in 2019 and has previous experience at Deloitte as a data analyst, as well as the petrochemical industry as a design engineer. Since joining BluESP, Kinesh has been extensively involved in various predictive maintenance and multivariate analysis projects for the petrochemical, mining, and metals industries. And last but not least, we have Koos. Koos has 20 plus years of experience and is the APM team leader at BluESP. He has extensive experience in electrical engineering and automation. He has worked in many industries, including oil and gas, food and bev, and various mining, metals, and minerals industries. Before joining BluESP in 2019, Koos was with Schneider Electric, where he worked as a solutions architect in the M industry. As you can see, these presenters certainly have a world of knowledge to share. Okay, we can move on to the agenda. On the agenda for today, Laura will first take you through an intro of multivariate analysis, delving into how ProMV can assist with production stability, a short demo of ProMV online, as well as a success story. Koos will then take you through some of the challenges faced by the different roles on site. And last but not least, Kinesh will walk you through the steps of quality prediction in a mining flotation plant using ProMV. I now hand you over to Laura.
Thank you, Raisa. As Raisa mentioned, my name is Laura Stridiron, and I'm in product marketing for AspenTech, focusing on the Asset Performance Management Suite. I've been with Aspen for a little over a year, or almost a year actually, and I'll admit I wasn't completely familiar with the APM suite when I started, but I quickly became enamored with the capabilities of our solutions and really wish that I had known about some of them earlier in my career when I was facing other challenges at other roles that I had throughout the industry. Woo, backwards. So all great solutions start with a really big problem, which is why I wanted to start with a little bit of the background about how ProMV came to be. Dr. John McGregor is one of the foremost authorities in big data and analytics, and he's the founder of ProMV. And during his research in big data and analytics, he realized that there was a gap in how analysis was being done. Multivariable analytics is very powerful, but the process of analyzing the data was lacking something really big. It was a big piece, which was the expertise, or something that I often refer to as a hidden factory of the users that would ultimately be impacting whatever the findings came to be. So put another way, what is that muscle memory and those actions that are taken just by instinct by some of the engineers and the operators that kind of is missing when you hand off big data to somebody that's not necessarily intimately familiar with the process? So Dr. McGregor saw that if we could put the power of multivariable analytics into the hands of a process engineer without them having to be a data scientist, we could truly unlock the superpowers of those that know that process inside and out. And the market noticed. You can see that the pedigree of some of the customers that have taken advantage of the solution. So what does this mean to how our customers do their job? Will mentioned we're in just an extreme state of what I'd call uncharted territory for some right now. Some are having to ramp down to a point where they don't know what their stability is. Some are ramping back up, and new monsters in the machines are popping up because it's a situation none of us have ever seen before. So it becomes even more important that those who are on the ground, the boots that are on the ground, are empowered to do the job the best that they possibly can. So in the case of challenges and tackling them without ProMV, let's use some examples of high energy losses or suboptimal throughput or scrap or off-spec product. And in this ramp up situation, you have an individual wanting to do their best and wanting to figure out what the root causes are. So they say, okay, I've got hundreds of variables across weeks, months, maybe even years. And so that's a lot of data. And then on top of that, I've got the non-process elements that really do factor into the final outcome. And this could be something like weather or who was the operator that day. And their tenure tends to play into things quite significantly. It boils down to that comes down to millions of combinations of variables to analyze. And this is just more than any human can do. And then even if you try and break it down to control charts, it's too many charts for operators to monitor and look at and compare. And you have the inconsistency factor of who was on shift and what decision does operator A make versus operator B, and similar when you talk about a process engineer. So as Dr. McGregor realized, most solutions available either required expertise to use in the form of either data science or familiarity with a particular piece of software, or it assumed that if you manipulate one variable, everything else stays constant, and we all know that that's not the case. So solutions like ProMV look across more variables from a multivariable sense. Process variability is another way to say you need process stability. So when there are efforts to create this stability, you can't control what you can't observe. And issues that creep into something like production quality may be due to things that aren't associated with quality or associated with your production stability, or even the item in question, because they're not currently monitored. And back to the comment earlier, uncharted territory, seeing new things. So we don't necessarily even know what we don't know yet at this point. With technology behind ProMV, customers can quickly identify the factors that are most critical to quality or the problem in question, and give more focus and insight to the efforts for plant support or even APC engineers for that matter. This could be examined across hundreds of process variables, and ProMV online capabilities then monitor behaviors amongst the variables to tell the user, the process engineer, the operator, when, we'll say, quality or throughput or yield might be at risk. This could be well before the thresholds of those particular parameters are triggered, and I'll walk through an example in a little while. The other capabilities to note are that some past ProMV customers find the ability to look for areas of opportunity within their process to see if they could make process changes to do something like, say, increase throughput. This allows the customer to push the limits of the capacity and meet demand without possibly sacrificing quality, but still increasing the amount of, say, sellable product that they get out the door. Once again, back to some of the challenges that Will mentioned earlier. The powerful benefits of ProMV, one of the powerful benefits is the ability to gain insight from process information that you've been collecting for years. Mining this information with ProMV will provide insights that aid in ensuring that process stability I mentioned earlier. The ProMV optimizer technology, which is part of the product, allows for quantitative definition of specific objectives. Then you can put variable constraints where you need of whatever is needed, whatever you want to tweak, and analyze this across hundreds of process components at a time. This puts the power in the hands of the process expert to zone in on what changes would yield the most desirable result. And some of our customers have seen pretty significant cost savings, as well as finding opportunities to tweak the processes offline and see what could happen before they run an online experiment. Now, when you're using the online portion of ProMV, it monitors, I mentioned earlier, it monitors hundreds of different variables that could indicate potential issues. It complements other operator and quality efforts in a few different ways. Because it monitors behaviors of process parameters relative to each other, not based on thresholds of the individual parameters, say temperature or pressure, the operators gain insights on what parameters to assess as opposed to just adding more charts to their screen. They're not constantly looking and trying to make dynamic decisions based on those individual variables. The process behavior analyzed with ProMV can be used as, we'll say, it's sometimes referred to as a soft sensor. So it could do something like predict quality, and I'll actually walk through an example of that later. And then when it indicates, hey, the process is acting in a way that is telling me, I'm speaking as a ProMV, the person is telling me that your product quality is going to be off spec, they can take action right then before it becomes off spec product. And then ProMV helps dive into what are the biggest contributors to why it's saying that. And I'll walk through that example in a second as well. And lastly, the interface, as I've just mentioned, it allows them to get a quick assessment to process parameters, to what process parameters are most heavily contributing to what's triggering the alarm. And then just to tie it all together, I wanted to highlight that information is only useful when it provides insights. Just showing data doesn't always help draw a conclusion. So not only is ProMV designed for, I call it messy data. That's a pretty broad term, but when you think of process data, it's passively collected. It's not always collected with a purpose in mind of being analyzed later. A lot of solutions that are out there require a significant amount of data cleanup, for example, even to be able to use, or they don't account for the fact that you go through pretty normal situations of in the chemicals world changing product grades on a regular basis. These are all things that impact the ability to effectively use an analytics solution. This means that, but ProMV is meant for that. You see the insights that are provided on the dashboard, but also with the models that are created, you could potentially replace a significant amount of individual daily reports that are reviewed. Anything that's manually compared with human eyes, we can put the power into ProMV so that it enables consistent decisions across multiple people, or the ability to more adequately prove out a problem when discussing it amongst a group. So I wanted to frame it up very quickly in a real world process. We didn't want to put up a live video to take a little bit too much time, but in this case, let's look at an LDPE production process. It has two jacketed plug flow reactors in series that are cooled by water. If you see this on the screen, there's about 20 different parameters that are being measured, but most notably, I wanted to point out the Tmax temperatures on both reactors, as well as the position of Tmax within the reactor. The status of the ProMV models is indicated either within ProMV, you can look at it in A1PE, or any other ODBC connection. So it doesn't necessarily have to be another screen that's up all the time. But once an alert is indicated, click through to the runtime dashboard, the ProMV runtime dashboard. Now on this page, there's a Pareto chart here on the left that shows the most significant contributing factors to what indicated that alarm. So in this case, the blue is that position, that Tmax position of the temperature in reactor 2. To the right is a time series plot of all these parameters. If I click on something within the Pareto chart, it brings up the time series associated with that. So in this case, I actually would have clicked on the position of T2. And then what it does is then I see the reference value of that parameter, the upper and lower bounds of that parameter, and then the actual time series value of that parameter. Now this dotted line is what ProMV was estimating that that value should have been. So this shows how the model is expected to perform versus how it actually was. And we can see from this trend that there's a significant deviation in what ProMV was thinking versus what actually happened, which is why the alarm was thrown. And the settings of how significant that has to be before an alarm are configurable. So as a result, the subtle shifts in the behavior of one or more of variables away from where ProMV expected it to be when they're detected, which is often well before that variable has moved outside of its univariate control limits, throws an alarm. And this is what makes multivariable process monitoring so much more powerful than univariate charts. And in this case, Z2, the position of the temperature within reactor 2, is moving further down the reactor than the model was predicting. So, but at the same time, the flow rate of the initiator injected into reactor 2 is remaining steady near the average value, while the model would have expected it to ramp down. And for these two control charts, we can reason that the reactor is, for lack of a better word, dying. The maximum temperature is moving further down the reactor, which can be caused by a decrease in the flow rate of the initiator, but that's holding steady. So we can infer that either we have a bad batch of initiator or that the reactor is having problems. So we have two things to investigate. This can all, and if you watch the live demo of this, that can be provided by one of our solutions consultants or by BluESP ESP, you'll see that all of this happens in under 10 minutes, and it's a very simple process. Another case that I wanted to highlight, I did mention earlier, is a company called ADM. It's an agricultural products company. The particular product that they were, that in this example, was something that they wanted to ship more quickly. They had demand for it in the market, and so the sooner they could get it out the door, the sooner they could realize revenue and the more they could sell. But they had a problem. Being able to ship it depended on a viscosity test that was done in a lab at the end of production. This lab test took between 2 and 3 days. So that meant 2 and 3 days of product just sitting there waiting. Then if it resulted in that the lab test came back that it was off spec, they couldn't ship the product. On top of that, 2 or 3 days had gone by. So they really didn't have a good way to be able to say, okay, one, when was this product actually produced? What was going on? So what was the root cause of why it was off spec? And then on top of that, what had changed in the process since then so that they could rectify the situation? It was really putting them in a you didn't know what you were going to get kind of situation. So using ProMV, what they did was modeled the process information against the output from the lab tests. Now they knew that it wasn't going to be exactly accurate because there's changes in lab procedures, testing techniques, the delay at the lab itself. But they figured they'd give it a try because one of the other things they had tried before was to add an intermediate test throughout the process, but they didn't find any kind of correlation to the final lab results. So that effort was scrapped. So it was a slightly longer analysis because of they were trying to back model a process to be able to predict quality. But as I mentioned, within 4 weeks, they were able to actually predict quality of the final output of the product. And then because it is machine learning technology, the more data they kept feeding into it, the smarter the model got. So now this is what they consistently use to predict whether the process is on spec, and it's going to produce on spec product. When an alarm is thrown, they can dive into what needs to be rectified and course corrected at that moment before it becomes off spec product. And they estimate this is saving them a minimum of $250 per year in off spec product. So with that, I will hand it over to the next speaker.
Hi everyone, Chris here. So I just quickly wanted to sort of look at some of the players that we have on site on a daily basis and the challenges that they face from a different aspect as what we've already sort of looked at, except maybe for our sort of directors of operation or senior VPs. They've got a different challenge apart from a day-to-day basis where they need to sort of improve overall operations. Industry 4.0 and digitalization sort of promises that you are able to sort of have better informed decisions and that you can also better predict and improve your process outcomes. Okay, but 3% of our industrial data is currently used out there in studies that has been done. And a large reason for this is purely the fact that we are struggling to separate our good data, our signals data, from the noise. Now that's the promise that ProMV brings. But like I say, there's more than just sort of the improving yield and so forth on site itself. There's our senior management really have pressure to sort of improve because there's no reason for them not to make use of the new technologies that's present today. Laura has covered a lot on the tool is focused around process engineers, and we've captured that. So I'm just stating that again, but the one that I want to focus is on the control engineer. So in the daily life of a control engineer, we basically, they develop, implement and maintain the strategies for control systems, and it's focused around the optimization of the operations, right? So that's clear. But there's a lot more that can be done on the background. So in a control system, we generate thousands of alarms. So in terms of that housekeeping and our alarm philosophies, we make it difficult actually for the operator on a plant to be able to review all these alarms that are available. And as Laura has mentioned earlier, we've got multiple other screens with charts. We've got our PCS screens. We've got APC screens on the side, as well as inspection information also. And this operator has to review and analyze and absorb all of this information. And now we're providing with alarm screens with thousands of alarms. So your control engineer basically has the ability to also push this information into ProMV. So that there's two major things that we can do when we analyze all the historical alarm events that we have from the past. And specifically, if we combine it with our historical process data. And that is that we can basically, first of all, we can see that the measures we've taken when we respond to alarms and how we respond to alarms, either by the operator of the system, what was the effect of that on our operations or on production? So, because classically, from a control system point of view, we'll purely look at alarms to be generated from the operation, and that's through the limits that we have from our process variables. And if as long as it's inside those limits, we're happy. But when we generate these alarms and we respond to these alarms, it does have an effect downstream and upstream of the associated equipment that generated that alarm. And we don't have a good understanding of this. And So we've got processes in place like first-up alarming and so forth to reduce our consequential alarms, but we still end up with many alarms and we don't have knowledge around these alarms. Now, that's where ProMV is quite strong and can help us. And we can also consider using the latent variables that's created inside ProMV to basically to alarm on these rather than the actual physical variables with 1,000 of variables that we have on site. And this will greatly reduce our alarm count. So, and this for the operator at the end of the day will make his life or her life also much easier in combination with the ProMV online environment where we are sort of guided as to how to operate. We can use ProMV to make sure that the information provided, the other information sources provided to the operator is also much cleaner and much more focused. With that, over to Kunesh.
Thank you, Koos. Hi, everyone. So I'll take you through a practical example of how ProMV can be applied in industrial processes. And simply, ProMV is able to sit on top of your data management layer, where you can use the data that you've been recording for years and start to mine the value from that data. So all of this works if you have the right amount of data, you have a good history of your process, and you also have quality measurements that you can actually tie back to your process. So in this specific case study, I'll take you through how quality prediction can be done in a mining flotation plant. So a mining flotation process is a continuous process used for selectively separating valuable minerals or metals from an ore pulp mixture. And you can see a diagram, a schematic of the flotation cell that's used. So in this application, flotation plants are designed to concentrate the iron ore to maximize recovery of valuable minerals or metals. And this is a common application in mining operations, but it's not only limited to this industry. We also see flotation plants used in paper recycling as well as wastewater treatment. So the objective of this study is to demonstrate how we can predict the amount of impurity in the ore before the lab result is actually measured. And often lab results take time to come back with results. And we can use ProMV to demonstrate how you can actually predict the quality before you reach that point where you have to make a process intervention. And if the impurity content can be predicted faster or earlier, it will provide process engineers or chemical engineers with actionable insights to adjust the process to reach the target quality. And this will help to maximize the economic value of your process. This will also reduce the amount of waste in the process, the amount of concentrate that gets sent to a waste or disposal. And this will also save costs in the long run. So just an overview of the flotation process and the data that we have available. In this specific plant, we have a flotation process which consists of multiple flotation cells. And these are agitated with air that's been supplied through the shaft in the middle. And the ore pulp mixture is sent through various cells to maximize your recovery, as well as the additions of surfactants or wetting agents, which are added to the pulp mixture when it enters the process. And this drives your particle interaction and attachment when it's interacting with the air. So the target particles then attach to the air bubbles and flow to the surface where they collect, and then your pulp mixture is sent through the system, through the cells, and eventually ends up in your tailings, which is your disposal. So the data used to generate a latent variable model or a model in ProMV consists of 2 data blocks. The convention is we have an X data block, which is your input, and these consist of initial conditions. And in this specific application, we have your quality measured at the start of your process, which is the quality of iron in the feed, and the amount of silica, which is your impurity in the feed. We then also have your process variables, which are tracked over time as the process goes from start to end. And these are your addition of pulp, the flow of pulp, the density, the addition of starch and amina, and as well as your flotation column measurements. And these are your flow of air as well as the level in the columns. And then lastly, we have our quality metrics, which is our Y variables. And here we're trying to indicate whether we can predict the amount of iron concentrate in terms of percentage in the end product, as well as the impurity, which is your silica concentrate in the end product. And the amount of data that we used is we used a sample of 26 data points. And this is because we want to predict our quality before a lab result is sent back. And so in doing that, we have initial conditions, which is the feed that is measured at the start of the process. These are measured in an hourly interval, same as your quality. And then our process variables are actually tracked in 30 seconds intervals. So that will give us an indication if we can maybe predict this quality within minutes rather than hours. So ProMV actually ingests this data as data blocks, as you can see. And if you look at the data just from a visual point of view and having a look at all of these variables, it's not really easy to see how they all interact together and what's happening at the same time, or tie it back to your quality. If you have a look on the right-hand side, there's many relationships that exist, a lot of different inputs and responses changing all the time. So how do you identify the variance in your process without a latent variable model? And this is where the power of ProMV comes into play. ProMV is able to reduce the dimensions of your model so that you can analyze fewer variables, but still hold the vital information of your process. And latent variable models are able to translate the information between the real world and the latent variable world to make it simple to understand what's happening in your process and without a loss of information. Aspen ProMV is also the only solution in the market that can do this while looking at different operating campaigns, variation in raw material feed, your seasonal conditions, and your operator influence in a single view. So the first step in ProMV is actually identifying the operating space and identifying all the different ways that the plant is operated in the past. The score plot is an indication of how your variables have interacted in the process over a given period of time. So in this specific example, you can see that the score plot is shown by the feed of, or the quality of iron in your feed that enters your process. And the colors actually indicate from low to high, from blue to red. And this also gives us an indication of how the process changes going from a raw material composition point of view. So the model accuracy is quite suitable for high frequency data set. We're looking at about 60% of variance that's been explained in terms of your R squared. And then we also have a similar accuracy in terms of your Q squared, which is the predictive power. So the score plot is actually displayed according to the first two latent variables, because these two latent variables or principal components explain at least 80 to 90% of your process variance. And here we can see the different clusters of iron feed indicating various starting positions of the observations that are being considered in this model. Next, we can also have a look at variable correlation, understanding key relationships which exist between the variables that you're analyzing. So in ProMV, we can test our model, or actually validate our model to see do the variables and how they interact together make sense from a process point of view. We also expect certain relationships to exist based on the laws of physics or chemistry, and that will govern the process as well. So in this particular plot, it's a loading plot which indicates the directions in which the variables move in relation to each other, and either positively or negatively. So the model here is telling us that our raw material feed, which is our quality of feed entering the process, whether it be iron or silica, is basically inversely correlated, meaning that when we have more iron entering the process, we have less silica, and vice versa. And this also holds true for our concentrate at the end process, is that we see that our iron concentrate is much higher at the end when our silica is less, meaning that we have less impurity. So in terms of the process variables, we can also see that some of the reagent flow also interact quite differently. Specifically, the amino flow is negatively correlated with the others. So the next step is now to understand how do we stabilize the process or identify the variance, and how do we, reduce the likelihood of that variance occurring. So to stabilize the process, we can look at the operating space and look at variables where the impurity levels were lower. And then we can look at the variables where the impurity, at the variables where the observations where the impurity levels were much higher. And then we can actually look at the contributions to that movement. What drove the process from a low impurity to a high impurity? And the contribution plot will then explain which variables caused this driving force, and will also give us an indication of how we can overcome this driving force. So this can be done for any variable that you have in your model. You can view the score plot according to your X variables, the inputs, and your Y variables, depending on the objective that you're trying to achieve. So now that we have mapped the operating space, we can see that the contribution from a low impurity level to a high impurity level is shown on the right-hand side. And these variables are displayed as weights, indicating their magnitude and direction in the process movement. So the variables that are below the x-axis were seen to be much lower when the process had high impurity levels, and the variables above the x-axis were seen to be much higher when the process had high impurity levels. So in order to achieve a lower impurity concentrate, this graph is actually telling us that we need to increase the variables that are below the x-axis, which is your reagent flows, your ore pulp flow, as well as the density, the starch flow, and the silica feed, for example. But on the other hand, we need to also decrease the amount of iron that's entering the process. But how much of this is possible, and is it physically possible? And that's where the model optimizer comes into play. So the model optimizer will actually tell us how much of this can we control and give a quantitative value of how we should control the process. So the model optimizer is a unique offering in Aspen ProMV because it allows the user to identify optimal set points which you could input to your plant and test against your model to see if you achieve the targeted outcome. And this is based on a PLS model, a partial least squares model. So the model is able to predict your Y variables from your X variables, but it's also able to predict X variables from the model. And in this particular case, the goal of the optimization was to minimize the impurity and also take into account the variable boundaries that exist in the model already. So setting the lower and upper bounds to the minimum and maximum of the model. And this will also allow you to set safety limits to your process, known values to variables that you are able to control, as well as for different raw material feed if you want to test it against different initial conditions to see how your process is affected by raw materials. And then you can set targets to your quality. So in this particular case, we look to minimize the impurity, but in doing so, we're also maximizing the amount of iron concentrate that will result. So as you can see there, this optimization ran and it actually gave us a list of all the X variables and a quantitative value of what we can use in the plant to achieve this quality. So the feature not only tells you how to change the process, but also provides a quantitative value as input to your operations. Another additional feature of this is that you can use this to develop new products based on your current process. Because it's an empirical model, you can actually push the boundaries of your process to see, can you develop different products within this model, and also apply this model to research and development. So lastly, we need to know, are we able to predict this quality, and how accurate are we predicting this quality? So we can test our model against unseen data by creating prediction sets. And this is where we leave some holdout data or unseen data to test our model against. And we can view the observed variables or observed observations versus a predicted observation for any variable that you've got in your model, whether it be an X variable and a Y variable, because the PLS model is able to predict both X and Y. And the model prediction accuracy for this silica concentrate is relatively good. We have a 90% accuracy. with a mean square error of both the training and the test data of less than 0.5. So this indicates that we have a suitable model to predict quality within minutes rather than hours, and with reasonable accuracy when you look at all the variables that are changing, as well as your raw material that's entering your process. So in real time, these models can be deployed and monitor your process continuously and give you prescriptive and real-time guidance on how to correct the process if it starts to move out of the boundaries of where you want to achieve the best quality or yield. So to conclude, this exercise or case study was actually analyzed in 3 to 4 hours, and that's less than a day. And this includes preparing the data, aggregating the data according to the structure that you need to predict, as well as analyzing all of these plots in ProMV. So the benefit here is that it helps the end user to analyze large volumes of data quite quickly, and it also adds to the domain expertise of the users. So my process knowledge of a flotation plant is very limited, but using ProMV, I was able to extract the key features and behaviors of this process and identify what causes the quality to change in certain directions, as well as to see which variables need to be changed in order to overcome these process upsets. So that concludes my portion of this presentation. I'll now hand over back to Riza.
Thank you very much, Kinesh, Koos, and Laura for that insightful information. We will now delve into our Q&A session. The first question I will direct to you, Laura. What special training or skill sets are required to be a power user of ProMV? Is data science as well as ProMV training needed?
That's a really great question. As I mentioned before, the genesis of ProMV was wanting to put the power of what ProMV does into the hands of process engineers. So being trained in ProMV is all that's necessary. You don't need a data science background. A general understanding of multivariable analysis is very helpful, but it's not required. We have a lot of customers that go through workshops with either ProCensus or ourselves, where we spend a week building models with them, and that's what's required to get up and running.
Okay, perfect. Next question to you as well, Laura. What is the average time between the start of analysis to results to recognizing the benefits?
So in a lot of these types of questions, the answers usually starts with an "it depends," because there's the complexity of the problem, how much data is being integrated. And so I mentioned in the example of ADM, where they were modeling the final viscosity to be able to predict quality online and in real time. That analysis did take about 4 weeks. But ADM also has an example of where they were tracking down the root cause of a quality issue in across 3 different dedicated product lines in a facility, and including data cleanup, data load, and analysis was under 5 days. So they were able to put that action into place and then take corrective action and see results in under a week.
Wow, that certainly is amazing. The next question is for you, Kinesh. Kinesh, you mentioned latent variables. Can you maybe touch on what is a latent variable?
Yes, sure. So a latent variable is simply a reduced dimensional model or variable. So if you could think of maybe 3 or 4 variables such as temperatures, which sort of move in the same way, one latent variable would actually capture all of those relationships that exist between the 4 and produce one latent variable. And this is how the ProMV model works, is it takes a large number of variables and reduces them to fewer number of variables, but each variable is basically encapsulating the behavior of X number of different temperatures or process variables acting together. And that's simply what a latent variable model means.
Okay, thank you, Kinesh. The next one is also for you. Does ProMV generate static or dynamic models, considering dynamics are capable of finding dead times and lags?
Yes, so in ProMV, you're able to actually specify a lag parameter. So you can choose an option where you can lag some of your variables if the time component is more specific to your process. And this will also allow you to adjust how much of the lag do you want. So it is dynamic, and it allows you to incorporate the temporal component of certain parts of your process if you need to lag certain variables.
Okay, thank you. Koos, I'll direct the next one to you. What is the difference between offline and online analytics? Could you maybe unpack a little about what you have used ProMV for in terms of the offline environment versus online?
So offline is looking at historical data. So we will review the historical data, clean it up, and build models out of that, all on that historical data. So, and once we have these models tested and tried, we will basically want to use them in real time. So from there, we'll connect it basically to a live data source, historian and other data sources, our LIMS and so forth, to basically to give us real-time guidance from that point onwards.
Okay, thank you. One more for you, Chris. How does ProMV handle batches of different durations when building a batch model?
So ProMV has a batch alignment function. So you can do simple linear alignment against time, so numerical optimization approach, or non-linear alignment. And it calculates the time versus maturity curve for each batch and add this calculated variable then to the project.
Okay, thank you, Chris. In the essence of time, if we haven't reached any of your questions, one of our APM consultants will contact you directly. And please feel free to contact us for any more information. With that, I will hand over to you, Wilhelm. Wilhelm, you are still on mute.
She was fast there, very, very fast to sort me out. Yeah, great event, guys. Great questions, great engagement from everybody. Thank you for staying with us for the whole hour. There was quite a few questions, guys, like, you're asking, is this event recorded? Yes, it is being recorded. So on the same link that you used to come into this event, you can refer back to it and you can see the recording. You can also share it with other people as well in your organization to have them also basically have a look at that. Yeah, and then you can see it's part of a series of events. So next week we're going, on the 1st of July, we're going to go more into the asset automation level. So looking more at IoT and and standards in automation, and also, do we do it in the cloud, and what automation do we leave, asset automation do we leave on premise, and when do we move it into the cloud, and topics like that. Throughout the session, we also basically said that there is, we have business consultants, so the likes of Ganesh or Koos or Rahisha or Laura available, that if you have any questions, they will contact you. We'll set up an IM call or a site visit and basically go through your requirements. So just after the event, you'll get an email, just reply on that and say, guys, I really would like to discuss this further. We also have a virtual training on these topics. So we have e-learning and virtual classroom training available when the COVID bans go lower again. Then we'll also restart with also local training here in our offices out of Johannesburg. So yeah, available the whole time. Yeah, and so I think thanks for the commitment and thanks for the time that you spent with us. look forward to see you in further events with us through the series. So we're halfway through. This is a 10-week series and we're covering lots of different topics. So yeah, let me end this one and see you in another webinar very, very soon. And also take the time to refer to some of the ones that we've already covered on Intel or on MES or on APC before. Thanks, everybody.